Hey everyone, we are Group Red 7 from Section 52, and this is our Project 1 for Physics 212. My name is Charlie, and my teammates are Tyler and Czar. For our project, we decided to focus on Problem 1. The problem statement is given as a box of mass m is positioned at the edge of a frictionless turntable of radius r that is rotating at a constant angular speed. An ideal string passing over a massless pulley and through a hole in the middle of the table connects the box to a hollow ball of mass m and radius r, with the string wrapped many times around the edge of the ball. Determine the angular speed of the turntable. The problem also provides the diagram, which is shown here. To solve this problem, we are going to analyze it with the strategies of a real-world context problem. This involves understanding the problem, calculations, and sense-making. We'll then talk about how this problem could apply in the real world, and a conclusion and reflection, and our references at the very end. To get started, we are first going to understand the problem. From the problem statement, we know the masses of the box and the hollow ball. M1, or big M, is the mass of the box in kilograms. M2, or little m, is the mass of the hollow ball. We also know the radius of the turntable and the radius of the ball. R1, or big R, is the radius of the turntable, in meters. R2, or little r, is the radius of the hollow ball, also in meters. These variables and their units are listed here. However, we need to find the angular velocity omega as a solution, which is unknown. Now that we know what the question is asking, we can make a few assumptions that apply to the situation. First, we could assume the turntable is frictionless, though this is already given. We can also assume both the string and pulley are ideal. An ideal string is massless, frictionless, and inextensible. We know that the pulley is massless, so we can deduce that it is also frictionless and does not accelerate. Finally, we'll assume the scenario is on Earth, allowing us to use the gravitational acceleration of 9.81 meters per second squared. With our variables defined and assumptions made, we can physically represent the problem. The diagram on the left shows how the three objects, the box, turntable, and ball, are spatially related. The box is at the edge of the turntable with radius r1. The string is attached to the box and goes through the middle of the turntable, where it is wrapped around the edge of the ball, which has a radius of r2. The diagram on the right is the extended free body diagram, showing all the forces acting on the system. For the box, it is pulled on by gravity, but this is counteracted by a normal force from the turntable. The box is also pulled to the right by the string, resulting in a tension force. Since the pulley is ideal, it simply changes the direction of the tension force and relates it to the ball. The ball is pulled up by the tension force acting through the string wrapped around the side. The ball is then pulled down by gravity through the center of mass.
Hello, my name is Czar and I'll be covering the calculations part of this problem. So, let's go over some key principles that will help us to solve this problem. We would need to recall that net torque, which results from the tension force on the ball, is equal to the product of moment of inertia and angular acceleration. Net torque could also be equal to the cross product of the ball's radius and force, or more specifically, the tension force. We could search up the moment of inertia and find it to be 2mr squared over 3. We also know that acceleration is equal to the product of radius and angular acceleration, which we could rearrange to isolate angular acceleration on one side to substitute it into the equation for net torque. Moving on, we could see from the free body diagram that its net force is equal to its gravitational force minus the tension force that acts upon it. We could find the tension force by solving for it from the net torque equation. Now let's examine the box's net force. Its net force would just be the product of its mass and acceleration, though we could also represent it as centripetal force, which is the product of its mass and velocity squared over radius 1. Furthermore, we know that its net force is actually just equal to the tension force it is experiencing. So, its tension force could be set equal to the equation for centripetal force. Then, to relate all of this to angular motion to find angular velocity, we could substitute velocity v in the box's net force equation from centripetal force to be the product of radius 1 and angular velocity. Now, let us actually solve for angular velocity. But first, we will need to solve for acceleration A for the ball. Its net force, which we will represent as m2a, is equal to gravitational force minus tension force. We could represent gravitational force as m2g, and then we isolate variable A. We all know the variables here, besides tension force, so we will solve for that next. We do this by setting the two expressions that we know net torque to be equal to one another, which is the product of moment of inertia and angular acceleration with cross product of radius and force, or in this case, the tension force. Substituting in what we searched up for moment of inertia and angular acceleration, we then simplify to solve for tension force. The radius will be cancelled out, leaving us with this equation, which we could substitute what we found for acceleration earlier into. After substituting what we know for acceleration, we can go ahead and simplify the expression to find tension force. We will need to distribute 2m2 over 3. Then we move negative 2ft over 3 to the other side, add ft's together to get 5 over 3 ft, divide by 5 over 3 on both sides, and we will end up with the tension force being equal to 2m2g over 5. Now that we know tension force, we could start analyzing the box's net force. We set tension force to be equal to the equation for centripetal force. We can then substitute in what we know velocity to be in order to relate it to angular velocity, which is the product of radius and angular velocity. Then from here, we divide both sides by m1r1 to isolate angular velocity. We take the square root of both sides, and we end up with the angular velocity being equal to the square root of 2m2g over 5m1r1. Now we can plug in some numbers. We aren't actually given values for the mass of both objects nor the radius, but we could come up with some numbers. So we will have the mass of the box be zero point 0.1 kilograms, the ball's mass will be 0.05 kilograms, and the radius will be 5 meters. Then for g, we already know that's just gravitational acceleration, which is, in this case, 9.81 meters per second squared. We substitute these values into our equation for angular velocity and get that angular velocity of the turntable will be 0.626 radians per second.
Having completed our calculations and determined a solution for the problem, we can then check out work with several sense-making strategies, which will be done by Tyler.
There are a lot of complexities that go into the equations. It can be difficult with all the numbers being thrown around and with the components to tell if the answers even make sense. So before beginning this question, we have to set up the real world context. So seeing that the units being found are accurate to the answer being found is one of the easiest steps for checking the work. In this case, it does seem confusing at first if there is a lack of understanding for what the angular speed means. Understanding that angular speed is equal to the product of the frequency and the constant of 2 pi can help with the final answer of 1 over seconds. And because that is frequency and is equivalent to radians per second, which is the correct unit, even though it's not technically a physical unit of measurement for the angular speed. Another important question to ask is if the numerical answer is reasonable. Since we know that our units are correct, the next thing we need to look at is the numerical values themselves. So it had been stated that the mass of M1 is 10 kilos and the mass of M2 is 5 kilos. The gravitational force is always 9.81 meters per second squared since we are dealing with Earth, and the final radius of the turntable we are using is 5 meters. And since we are solving for angular speed, our answer came out to be 0.626 radians per second. And in this physical context, the answer is supposed to represent how long it takes for the turntable to complete one full rotation. Clockwise or counterclockwise do not matter in this situation. So by dividing our answer by 2 pi, we can determine that it would take about 10 seconds to complete a full rotation of the turntable. And thinking in practical sense about the weight and also the radius of the table, and just if you're imagining this, how this would look, it makes sense. And so just by thinking practically, like a wooden box attached to a tennis ball and a record player, it makes sense. When talking about physical sense, it goes back to thinking about what sounds reasonable based on our already existing knowledge of this subject, as well as our real world sense making about visualizing the problem and using that knowledge in correspondence. A good way to think about this is the special case analysis, which is setting the mass of 0 kilos, which is just there to make it's no objects at all if it has 0 kilos, which there just be infinite angular velocity because there is no mass acting on the system anymore. Additionally, there are a lot of real-world examples that use the same techniques in this problem. Is it that if they involve the rotation of an object with a mass that is also rotating with a mass attached to that primary mass? So the applications of angular speed slash velocity in this other example is a tetherball, which follows the same principles of the turntable in terms of angular speed and velocity. And the motion is somewhat similar, but it would follow a similar, or even possibly in certain cases, the same equation.
The final part of our presentation is our conclusion and reflection. After finishing this problem, we were able to take away several key concepts. The problem highlighted the importance of extended free body diagrams, where forces are positioned in the correct spatial arrangement to each other. This is especially necessary for calculating torque, which is similar to the baseball bat problem in homework 2. In this case, the center of mass had to account for the torque generated on either side of the center point. A larger mass needs a smaller torque arm, and a smaller mass needs a larger torque arm to balance out. Without an extended FBD, this won't be clearly seen. This also allowed a combination of force and torque analysis to connect all the equations. The torque was especially useful as it determined the impact of the tension force due to the ball. In studio activities, it was fine to analyze the acceleration of two spools suspended from a pulley with net force alone. However, this changes when there's only one spool, or in this case, one ball, and the other end needs to be fixed. Finally, the problem also demonstrated how centripetal acceleration and angular velocity are related, which is through translational velocity. This is a key concept in many physics problems, where equations need to be derived and connections have to be made to substitute them. Overall, we had fun solving this problem, and we hope you enjoyed it too. These are our references, which we use to find the moment of inertia of the ball, the weight of a normal tennis ball, and the picture of a tether ball in real life. Thank you for listening.